This meeting is being recorded.
Welcome everyone to this Monash Cybersecurity Seminar. Today we are very happy to welcome Stephen Galbraith from New Zealand. Professor Galbraith has a bachelor's degree from the University of Waikato in New Zealand, a Master of Science from Georgia University of Technology in USA, and a doctorate from Oxford University in the UK. He held research positions at Royal Holloway University of London, University of Waterloo, the Institute for Experimental Mathematics, Essen, and the University of Bristol. He moved to the University of Auckland in 2009 and is currently the head of the mathematics department there. And his research is in computational number theory, computational algebraic geometry, and applications in public key cryptography. Currently, he is mainly interested in post-quantum cryptography, and he is an international leader in mathematics of public key cryptography, and wrote a large book with this title that was published in 2012 by Cambridge University Press. And today he will talk to us about zero-knowledge proofs of Isogeny. Thank you very much, Stephen, and the scene is yours.
Okay, so I have to reshare my screen, I guess.
Yep.
Cool. Yeah, sorry I was a bit late. I'm having a busy day. Thank you for the invite. It's very nice to be here, and I'm going to talk about some joint work with students, and also I'm really giving an overview of lots of work by many people. So this is the plan that I'm going to try and get through. I'm going to start off by talking quite generally about graph isomorphism and some quite general problems in graphs, and then I'll specialize to isogeny graphs and talk about some specific proofs. So everyone's hearing me okay and seeing everything?
Yep, all good.
I assume so. Well, I think everyone knows what is a graph, vertices and edges, so I won't spend much time on this. But just to remind you, a graph isomorphism, is a bijection on the vertices that maps edges to edges. And is a very standard example of a zero-knowledge proof is proving that you know an isomorphism between two graphs. So we think of these two graphs as being public. Suppose these two graphs are in the public domain, or at least some people know about them. And I happen to know an isomorphism between them. And I want to convince you I know this isomorphism, but I don't want to tell you what the isomorphism is. I mean, I can always convince you of my knowledge by telling you my knowledge, but sometimes I want to keep it private. So this is a very standard argument. What do? I compute a new random isomorphism from the second graph to the third graph, and I give you this graph, and then so that's a commitment, and then you send me a challenge. And if the challenge is 0, I reply with the random isomorphism I just chose, and if the challenge is 1, I reply with the composition of the two isomorphisms. So this is now an isomorphism from the first graph to the third graph. And then you can verify that I have answered your challenge correctly. And then we repeat this protocol many times. And after we've done this many times, you start to believe that I do know an isomorphism between these two graphs. So this is it. Pictorially, I have the graph, the first graph, and then the second graph, and then an example of the commitment would be the third graph at the bottom. And depending on the challenge, I give you the C, or I give you the composition C composed with phi. And the idea is if I can always give you an isomorphism from either the first graph to the third graph or the second graph to the third graph, then I must know an isomorphism between the first two graphs. And then the idea that this doesn't leak any information about my secret is that all you see is a third random graph, and all you see is an isomorphism either from the first graph to the third one or from the second graph to the third one. So that from the verifier's point of view, the idea is that this shouldn't be revealing the secret. But I'm going to go through this argument more precisely a little bit later. So this is two security properties we're focused on is soundness, which is that you're convinced I do know an isomorphism between these graphs, And so that's security from the verifier's point of view. The verifier wants to know that they're not being tricked, that they really are being convinced of something. So that's soundness. And then zero knowledge is security from the prover's point of view. The zero knowledge means that it's not leaking information about this secret isomorphism. So let me go through a bit of formalism. So this is not a very good example in practice because it's very annoying having to repeat this protocol many times. And also graph isomorphism is not actually a very hard problem. But let's not worry about that. Okay, so now I'm going to give some more theoretical computer science formalism. So what we're really interested in is relations or languages. And we have something called X. So X is a statement. It's a claim that's being made, and W is a witness. So in the graph situation, X would be the pair of graphs, the first graph and the second graph, and the witness is an isomorphism between them. And in the context of my talk, I'm interested in hard relations where it's hard to compute a witness. If you're presented by an instance X, it's hard to compute a witness. But I'm also interested in ones where you can efficiently generate examples. So in the case of graphs, I can write down a random graph and I can write an isomorphism. So I can efficiently construct a pair of graphs that are isomorphic. That's easy. But if you just give me the two graphs out of the blue, it's hard for me to construct the isomorphism. And I'm interested in these three-move protocols. So there's a prover and a verifier. So both of them know the public statement X. Only the prover knows the witness. And so the prover is trying to convince the verifier that they know the witness. And there are these three steps. There's first what is sent as a commitment from the prover to the verifier. The verifier responds with a challenge, and the prover sends a response. And then the verifier runs an algorithm that takes the instance of the problem, the commitment, the challenge, and the response, and either accepts the proof and says, yes, I'm convinced by this, or rejects the proof and says, you're cheating, or you don't know the witness. All right, so this is very standard formalism. And then I can more precisely define soundness. So soundness is about, again, that's the idea that the verifier is convinced of something. And soundness, the idea of soundness is, suppose I've got a response to a challenge, and then I've got another response to another challenge, and these two challenges are different. Challenge prime is not equal to challenge, but they're on the same commitment. So notice here, I've got an accepted, right? The verification algorithm is accepting commitment, challenge, response, and it's also accepting the same commitment. This is not a typo. The second one is the same commitment, different challenge, different response. So what soundness means is if there's an extractor algorithm, there's an algorithm that will take these two accepted transcripts and will compute a witness. So you can really derive a witness from these two accepting transcripts. So that's a sort of precise definition of what soundness means. And the way this is used in proofs is by a rewinding argument. So you imagine there's someone who's a prover who can convince you of this protocol, and you run the prover, and they give you an accepting response to your challenge, and then you rewind them just back to the moment before you sent the challenge, and you reply with a different challenge. And if they can still respond correctly, then you end up in this scenario where you have two different responses to two different challenges on the same commitment. Now is probably a good moment to stop in case someone has an urgent question about the meaning of soundness or Sigma protocols. I can't see the chat, so I've got no idea if anyone's put anything in the chat.
No questions so far. Yeah, I'm
Okay.
looking at it.
Good. And now what is zero knowledge? So that was the soundness, which I stress again, that's about the verifier. That's about the verifier being convinced. And zero knowledge it's the provers. The prover is worried about this. The prover wants to know that it's not leaking any information. And so zero knowledge is formalized by having a simulator that can generate these transcripts of the protocol. So, and this is quite a strong notion that I got from this survey by Damgaard. There's a simulator that, given any instance of the problem X and given any challenge, will output a commitment and response. So essentially the prover's side, the commitment and the response can be kind of manufactured simultaneously to satisfy a verifier. But this is not violating the protocol, because in the protocol, the commitment is sent first, and only after the commitment is received is the challenge sent by the verifier. Whereas in this case, we're flipping it around. We're asking the verifier to give the challenge first, in which case I can come up with a commitment and response. So this is not in conflict with the proof of knowledge. And we'll see in this talk examples of statistical zero knowledge, where the transcripts are identical or very closely distributed to the real transcripts. But also, unfortunately, with isogenies, we have schemes that are only computational zero knowledge. So we can simulate transcripts without knowing the witness. Yeah, I guess the thing I should stress, the simulator does not know the witness, right? Obviously, if you know the witness, you can run the protocol. But the formalism of zero knowledge is that you can construct transcripts without knowing the witness, as long as you break the ordering commitment challenge response. And I'm not going to talk about witness indistinguishable. Okay, so let's go through this very precisely now. So we've got our graph isomorphism problem. We've got this picture. So in symbols, our instance is the pair of graphs, the first graph and the second graph. And our commitment is a third graph, right? And the prover knows the witness, which is the map phi, and the prover is also constructing this map C as well. So that's what the commitment is, the third graph. And the challenge is the single bit. And if the bit is 0, the response is C. And if the challenge is 1, the response is the composition. And so what is the verifying algorithm? The verifying algorithm takes the instance X, the commitment, the challenge, and the response, and it verifies that the response really does provide an isomorphism between either V1 or V2, depending on the challenge, to V3. And checking an isomorphism means you check you've got a bijection on the vertex sets, and you check that every edge maps to an edge and vice versa. All right, so that's the verification algorithm. So let's prove zero knowledge, and then we'll prove soundness. So why is this zero knowledge? Well, I claim that the responses, even if you don't know the witness, you can answer this. And the reason why is because when you see a response, it's either a uniformly chosen graph isomorphism from the second graph to the third graph, because that's what it says on the second line, uniformly chosen isomorphism. So in the case where you're responding to the challenge 0, you get a uniformly sampled isomorphism. But I also claim when you're answering the challenge 0, you're also getting a uniformly sampled isomorphism because phi is fixed. But we're just talking about permutations of finite sets. If I fix a permutation of a finite set and then compose with a uniform permutation on a finite set, then I get a uniform permutation on a finite set. So just viewed in isolation, because the verifier only gets one, either gets C or it gets C composed with phi. Looking at one of those things in isolation, either one, they're uniformly distributed. So that means I can simulate. Because if I know the challenge in advance, I just write down a uniformly sampled graph isomorphism from either the first graph or the second graph, depending on whether you're challenging me with 1 or 0. And so I can write down these graph isomorphisms that are distributed exactly the same as in the real protocol. All right. So the key point is that even if one of the isomorphisms is fixed, when you compose with a uniformly sampled permutation, you get a uniformly sampled permutation. And if there's more than just a permutation, if there's edge choices, same thing. The uniform choices compensate. All right. So that's why you get perfect statistical zero knowledge. What about the soundness? Why is this protocol sound? Well, suppose I can get a response to two different challenges. Well, since the challenges are only 0 and 1, I've got a response to the challenge 0, and I've got a response to the challenge 1. So I've got the isomorphism C because that's the response to challenge 0, and I've also got the response to challenge 1, which is some isomorphism from the first graph to the third graph. Now, at this point, I don't know that that is C composed with phi because I'm the extractor, and I'm still yet to be convinced that the prover knows the witness. All I know is that the prover can compute an isomorphism, graph isomorphisms in both directions. So all I need to use the fact now is that because C prime is an isomorphism and inverse exists, because C is an isomorphism and inverse exists, that's part of what I verify. I verify that it's an invertible map, so I know it has an inverse. And I know that if I compose a map from the first graph to the third graph with the inverse of a map from the second graph to the third graph, if I compose those maps, I get a map from the first graph to the second graph. And by definition, well, you can show that this will also be an isomorphism. So the extractor, I don't need to think about whether the prover knows a witness or not. The extractor is building a witness out of the proof. Okay, so it's very important that this little proof, these last 4 lines, it's very important that this does not presuppose the existence of the witness phi. It's proving the existence of the witness phi on the basis of the evidence that the verifier has. Any questions about that?
I have a question, Stephen.
Mm-hmm.
Okay. So I assume the second bullet point here, commitment scheme, that one, it's probably hiding and binding, right? You need both hiding and binding from the commitment?
In this case, in the case of graph isomorphism, no, I know that. You just give the graph. You just give the graph. So this is just a graph. There's really a question about the hardness of the relation, whether this is hiding. In this particular instance, graph isomorphism was quasi-polynomial, so this is not actually necessarily hiding.
Yeah. All right. Because my main question was how computationally costly is to calculate such a commitment.
Yeah. No, I think I'll come back to this. That's a good question, and I'll come back to this in a few moments when I talk about graph theory problems in general.
Sure.
Yeah.
Thank you.
So within the sort of the world we're in now about what is graph isomorphism, a graph is represented as adjacency list or an adjacency matrix, and all these things. Writing down the isomorphism is writing down a permutation or a table of values. These are all quite large representations. But that's if graph isomorphism is the problem you're interested in, then you're doing very traditional graph theory of algorithms running time being at least linear in the number of edges. So here's an interesting problem. What about not an isomorphism between two graphs? Let's just fix one graph and take 2 edges and talk about, can I find a path between 2 edges? So what is a path? It's just a sequence of edges where it starts at V and the end point of the first edge is the start point of the second edge and so forth. Is there a way to prove knowledge of a path in a graph without revealing the path? So I claim there's the obvious thing. If you're looking at this picture and now you've just got one graph and you're thinking of paths in the graph, the obvious thing to do is you want to prove a path from V to W, The obvious thing is you make a path from W to some other new random vertex called a W prime. And if the challenge is 0, you publish that path. And if the challenge is 1, you publish a path from V to W prime, which you know because you know a path between V and W and a path from W to W prime. So that's kind of the obvious way of proving a path, using a picture that's somehow similar to that. But this is completely wrong. Why is it wrong? Is someone going to explain? Excellent. People are confused.
The path goes through V, right?
The path goes through V. So when you write down, I wish I could highlight. If I click, it just changes to the next slide. If you respond to challenge 1 by writing the composition of these two paths, then the person who's verifying it will notice that the prefix is the secret. So that's no good at all. And actually, I don't know a solution to this problem in general, but this problem is actually not interesting because there's a polynomial time algorithm to find a path in a graph. I mean, this is something we teach in every discrete maths course. You teach Dijkstra's algorithm that even finds the shortest paths. But what I want to slightly shift the narrative. I want to look at graphs that come from families that have a compact representation, but the graph is very large. So this is coming back to your question. In traditional algorithmic graph theory, when an algorithm takes as input a graph, it's usually the representation is usually linear in the number of vertices and the number of edges, because it's given by a list of incidences or a matrix or whatever. So normally in graph theory, you're looking at algorithms where the input size grows with the number of vertices and the number of edges. And so polynomial time complexity means anything polynomial on that. So if you've got graphs of a million vertices, then anything whose running time is a million or a million squared or a million cubed is all polynomial time. And that's fine if you're a graph theorist. But if you're a number theorist, you can think about families of graphs that have a very compact description, but the graph can really be very large. So you can end up with graphs where the size of the graph is exponential in the length of the description. Now, for such a graph, the graph isomorphism problem may be interesting or it may not be interesting. You could ask whether two graphs are isomorphic given their compact descriptions. But the reality is that if you have a situation like this, then where the graphs are exponentially large relative to their description, it's actually very unlikely that you will end up with two isomorphic graphs because you're generating huge graphs, a small number of huge graphs, so they're probably not isomorphic. But this path problem is definitely interesting. If I have a way of generating huge graphs with a compact description, I can also write down two vertices in this graph and challenge you to find a path between them. Whereas I know it because I just generated the second one by taking a path. So it's very natural to think about proving knowledge of a path in a graph. And actually, I don't know if anyone has ever considered this problem before for general graphs or for say general expander families. And this only occurred to me this week as I was preparing the talk. So I think it's an interesting question for people to think about. Is there a way to give a zero-knowledge proof for knowledge of a path in a graph, where the graph has exponentially large relative to its description? So that's an open question. Right, so what are these graphs? I'm now going to tell you an example of a graph which has whose size is exponential in the length of its description. And those who know me will know that this is to do with elliptic curves. It's just one slide, really. This won't help you much if you've never seen anything about elliptic curves before. But the vertices in the graph are going to be isomorphism classes of elliptic curves, whatever that means. So the objects in the graph are some number theoretic object, which is actually a group. So each vertex is corresponding to a group. And the edges in the graph are going to be these things called isogenies that are maps in the sense of geometry. They map the points on a curve to the points on a different curve. And they're also group homomorphisms. So here's, just to give you a flavor, here's an example. We have two elliptic curves. These are somehow apparently not the same curve. They've got different equations. And I've written down this thing, phi, which is given by some rational functions. And I claim that this is a group homomorphism. That's not obvious. And it's a group homomorphism with finite kernel, and the kernel is just a subgroup of order 2. So the kernel of this isogeny has size 2. And so this is called an isogeny of degree 2 or a 2 isogeny. Anyway, these are the kind of things we're talking about. So the vertices, so E1 and E2 are going to be vertices in the graph, and phi is going to correspond to an edge in the graph. So there you go. There's a beautiful hand-drawn description of a 2 isogeny graph. So each of these edges, so in general, there's going to be 3 different choices of subgroup of order 2, cyclic subgroup of order 2, and so you get 3 edges. So these graphs start off being kind of tree-like, but they're not actually trees. They will have cycles in them. So is there any questions about what is an isogeny graph?
That was in fact my question that you answered at the very end. So they are generally not trees, right?
No.
But any other graphical structure you can?
Well, then this depends a little bit. There's really 2 worlds of isogenies. There's the SIDH world and there's the seaside world. And the seaside world is got much more structure. They're really Katie graphs or Schrei graphs, so there's really a group acting on them, and they have a lot of structure. But actually, mostly what I'm going to talk about in this talk is more of this kind of thing, where these things. This is the supersingular, the full supersingular isogeny graph, and there's not a lot of apart from the sort of locally tree-like property, there's not a lot of sort of global structure. They become pretty ugly and pretty random. They look pretty random. And the fact they're expanded graphs means there's a short path between any 2 vertices. So you know that if you've gone too far down this binary tree, there will be a shorter path between these vectors than going back up the way you came.
There is another question in the chat, Steven. I can read
it.
Why the point 0, 0 has order 2?
That's a factor by the elliptic curve. So this is a point that's equal to its own inverse. So you have to understand the elliptic curve group structure or the group operations to see that. So yeah, if you've seen much about elliptic curve cryptography, you've probably seen the elliptic curve group law, and that's what I'm using to get that fact.
Okay.
Yeah, so this slide is really about saying that I need this to explain SIDH, that somehow isogenies and kernels, you can understand isogenies just by understanding the kernels. So given a subgroup, there is an isogeny with that kernel. So isogenies are essentially determined by the kernel, and there's a reasonably algorithmic way of working with them. But the running time is linear in the size of the kernel. So what you really want to do, the reason why we like to study 2 isogenies is it's actually not hard to find a 2 isogeny between 2 curves. In this example, if I give you E and EA, they're connected by an isogeny of degree 8, which is a composition of isogenies of degree 2. Obviously, this is a small example, and you could try all possibilities, and you could find the isogeny from E to EA. So what I'm interested in is isogenies of quite large degree, but to make all this efficient, I'm going to compute them by composing lots of isogenies of degree 2. And SIDH also use isogenies of degree 3. But it's important for efficiency reasons that we work with isogenies that factor as a product of small primes. Right, so here's Galbraith, which is fairly hard to understand if you've never seen it before. And the key is that it uses elliptic curve with a very special group structure. And the key point is, this is the 4th bullet point. Alice, her secret is a subgroup of order 2 to the n. And Bob, his secret is a subgroup of order 3 to the m. And 2 to the n and 3 to the m are about the same size. So Alice has a secret subgroup, and that means she has a secret isogeny, phi sub a. And Bob has a secret subgroup, and he has a secret isogeny, phi sub b. And when they send to each other, Alice sends to Bob the image of her isogeny and the image under her isogeny of some points, like these points, PB and QB. All right, so what does Bob see from Alice? Bob sees the curve EA, the image of E under her isogeny, and the image of these points, PB and QB. And similarly, Alice sees the image of Bob's isogeny and the image of some points under Bob's isogeny. But the important point is they keep their isogenies secret. Alice's secret isogeny, phi A, only she knows. Bob's secret isogeny, only he knows. And the idea, the reason why you send this extra information, these extra points, is that it allows this commutative diagram to be formed. So Alice knows the vertical line at the top. She knows phi A. But Bob gives her enough information to push the kernel down through phi B so that she can compute the second horizontal arrow. Right? So she chooses her arrow first, and then from the information Bob gives, because Bob gives these points, phi B of PA and phi B QA, she can compute the image of GA, her subgroup. She can just compute it. She can compute phi B of GA. And that kernel gives her the bottom horizontal arrow. And simultaneously, Bob, he knows the vertical arrow on the left. And because of the information Alice gives, he can compute the vertical arrow on the right. And so both of them can compute these extra arrows. And then the magic of mathematics, they both lead to the same curve, because whichever either you go along the top and down or down and along, you're in both cases quotienting out by the subgroup GA and the subgroup GB. So you're quotienting out by the group generated by both kernels. And so you must end up at the same place because, like I told you, the isogenies are determined by the kernels. So that's SIDH in 2 minutes. It's a bit hard to get your head around if you haven't seen it before. But that's the protocol. And this was submitted to NIST, and it's made it to the third round as an alternate, or I mean, a key exchange scheme based on this, or a KEN, is still an alternate in the NIST post-quantum standardization. So it's still very much a thing that people are interested in. So sorry, that was really quick. And what I'm really interested in now is this is the key exchange scheme, but now this protocol also has a lot of other uses. And what I'm really interested in is this idea of Alice proving that she knows this isogeny, phi A. So how can Alice really prove that she knows this isogeny? Or how can Alice prove she knows any isogeny between two curves? And this is closely linked to isogeny-based signature schemes. And so this is kind of the state of the art at the moment, or a summary of where everything's at. So Jiao and DeFeo published this key exchange scheme that I just talked about. And then in a later paper with Ploot, they described a Sigma protocol for Alice to show that she knows the isogeny from E to EA. And the Sigma protocol was then used for signature schemes by two different groups. So Yu et al. And a paper of mine showed how to get this kind of instant signature scheme from this. Another paper with Petit and Silva, we came up with a different signature scheme based on a different problem. And then there's this really cool thing called ski sign. And then there's also work by LaRue, which is about showing knowledge of an isogeny. And all these things are working in, I would say, the seaside setting. They're working in the general isogeny graph. And then there's a whole other part of isogeny cryptography, which is based on group actions, which is called Seaside. And within that, there's various papers on, again, mostly focused on signatures rather than zero-knowledge proofs. So there's various, well, basically the same idea, going through different flavors of signature scheme. Now, there's no way I can cover all this content especially since I probably want to finish in 15 or 20 minutes. So I'm really just going to focus on the first bullet point. So if you want a whole series of lectures, there's more than enough to cover, but I'm just focusing on this, the Sigma protocol from SIDH by DeFeo, Zhao, and Plut. There's lots more that could be talked about. Any further questions at this point?
I think there is not a question, but maybe a comment in the chat. So this one is ZK path proof might be reducible to a ZK graph isomorphism proof. Find an isomorphism of a graph, prove with ZK the isomorphic graph is isomorphic, and give the path in the isomorphism.
Yeah, exactly. But I think the problem is that you want to look at this problem in situations where the graph is too big to ever think about proving graph isomorphism because it's exponentially large, but the path problem still makes sense. So I'm interested in the case where the graph is exponential, but the path is polynomial length. So how do you prove in polynomial time a polynomial length path in the graph, even though the standard proofs of graph isomorphism or Hamiltonian cycle would be exponential complexity? So I'm really looking for something new. Yeah, it's a good question. All right, so let me, I think I'll skip that. All right, so let me explain the basic Sigma protocol from the paper of DeFeo, Zhao, and Plut. And it's very simple. You want to prove, so the prover knows an isogeny between E0 and E1. And let's really think of this about SIDH. So E0 is what I called E, E1 is EA, and this isogeny phi has degree 2 to the n. So this is a 2 to the n isogeny between E0 and E1. And in this context, they also assume that there's 2 points on E0 and you can, or actually you don't need it. So yeah, I'm just going to prove that I know an isogeny of degree 2 to the n between E0 and E1. So what does the prover do? The prover follows SIDH. So the prover computes a 3 to the m isogeny, psi, and also does, just like what they would do in SIDH, maps that kernel across to E1 and computes the corresponding isogeny. So psi and psi prime have degree 3 to the m. But apart from that, are arbitrary. So you've just essentially chosen an arbitrary subgroup of E0 and computed the corresponding isogeny, and you've mapped that kernel across and you've computed the corresponding isogeny. And you've got to 2 new curves, E2 and E3, and that's the commitment. All right, so the commitment is E2 and E3. And following SIDH, there's also, the prover can also map the kernel of phi. It knows the kernel, it knows the witness, and it can map that kernel down under psi, and that gives you the exact commuting square from SIDH. So the prover knows all this, but the prover is not giving it away. They're just giving away the commitment, E2 and E3, these 2 curves. And so the verifier sends a challenge. If the challenge is 0, the prover basically opens the kernel of these 2 isogenies, psi and psi prime, so the verifier can check. Yes, it is true that this response, the response gives me an isogeny from E0 to E2 and an isogeny from E1 to E3. And if the challenge is 1, the prover reveals the kernel of phi prime, and the verifier can again be convince themselves that they have an isogeny from E2 to E3. So so this is the protocol from their paper. Commitment is the 2 curves E2, E3. If the challenge is 0, the response is the 2 vertical lines. If the challenge is 1, the response is the horizontal line along the bottom. And the claim in their paper is that this is zero knowledge because you can simulate it, and this is sound. So again, of course, you have to repeat this many times, and you'll repeat this for random commitments. But there's already a bit of a trap with the zero knowledge. You need computational zero knowledge because you need to it's non-trivial to know, without knowing the witness, you can't be sure that you actually somehow have a square of the right form. So you really, when you're doing the simulation, you're either knowing the challenge is 0 and computing these vertical lines. And then you don't actually know they're parallel. And if the challenge is 1, you're really just choosing a random curve E2 and a random isogeny to a curve E3. And you've got no idea if that line is in some sense parallel to the witness, if it exists. So the point is when you're doing the simulation, you don't know that these lines are really truly parallel, and you don't know that this phi prime is really parallel to the witness if it exists. So you end up with a computational assumption that says that it's hard to distinguish these cases from the real thing. But the real issue is soundness. Is this a sound proof of the witness, right? Because that's what we want. We want soundness. We want to know that this proves a witness. And this is where things get a little bit murky, because it depends on what is your definition of a witness. If someone has responded to both challenges for the same commitment, then you do have an isogeny down and an isogeny log. I think I've got some on another slide. Yeah, so if someone's responded to both challenges, you have the 2 vertical isogenies and you have the one along the bottom. And so if you compose with the dual, which I haven't explained, but it's just the arrow going the other way, if you compose these 3 maps, you definitely get an isogeny from E0 to E1. So there is definitely an extractor that, given one commitment and the responses to both challenge 0 and 1, definitely there's an extractor which extracts an isogeny from E0 to E1. So it does prove the existence of an isogeny from E0 to E1. But it does not allow you to make any claim about the degree. Well, it tells you that isogeny will have a certain degree, but that's maybe not the degree you're looking for. And so Giardefeo and Plout essentially claimed that this was sound, that if the witness had degree n, then this proves the existence of an isogeny of degree 2 to the n from E0 to E1. And unfortunately, this is just simply not true. So I can, suppose I'm a malicious prover. A malicious prover can start with a curve E0, can construct an isogeny of degree 3 to the m to a curve and say, I'm going to call that E2. Can construct a 2 to the n isogeny from E2 to E3, and then construct a random 3 to the m isogeny from E3 to E1. And now if this malicious prover wants to convince the verifier that they know an isogeny between E0 and E1 of degree 2 to the n, then they will always, they will just reuse the same commitment. This is about, I'm not talking about zero knowledge now, I'm talking about soundness. So here's what the malicious prover does. The malicious prover, in every iteration of the protocol, uses the same commitment, E2, E3. And if the challenge is 0, it answers with psi and psi prime. And the verifier checks, yes, these are isogenies from E0 to E2 and E1 to E3. And if the challenge is 1, it answers with phi prime, and the verifier accepts that is a correct response to the challenge 1. But there is no isogeny of degree 2 to the n from E0 to E1 because these 2 slides aren't parallel. So this is a counterexample to showing the existence of an extractor that would reveal an isogeny between E0 and E1 of the correct degree 2 to the n. Of course, there's an extractor that reveals an isogeny, but it's not preserving the degree. So that we noticed that a couple of years ago, and then there's also a paper by Gantos, Pintori, and Veroni, which has a similar problem with the extractor. And this applies even in the case where the sides are vertical. And so there really is a witness of the correct degree, and you can push that witness down, and you get, oh, this is the, I don't like this notation, sorry. And you push this witness down, and you really do get, consider the top arrow to be the one that, that is the sort of push down of the witness. But when I'm doing the proof, if I'm a malicious prover, I'm going to answer with this curly phi instead. And now if you try and run the extractor and you try and pull the way the extractor works by pulling the kernel back, you end up constructing a sorry, you end up constructing an arrow going the wrong way. So if you follow the Joule-de-Feo-Ploot extractor, you end up in this case by a Gantt-Ossenal, you end up with an isogeny in the wrong way. It's going the wrong place. So that's also an issue with the sound. So there's two problems with the soundness proof. Well, it's just not sound. It's not a sound proof. All right, so we fixed this, and you really have to somehow force this parallelness. And what this means is you've really got to make sure that I mean, what does parallel mean? It means that you take the kernel of one of these maps. The sides being parallel means if you take the kernel of one of them and you push it forward along through one of the horizontal ones, you do get the kernel of the down one. And that's also what I mean by saying that the two vertical ones are parallel. What I mean is if you take the kernel of the top parallel line and you push it down through the vertical map, you do get the kernel of the next horizontal. So that's the requirement the square commutes. So that's not being checked in the protocol in the present form. So the way the protocol works is you have to enforce this. So I'll very quickly say the tweaks. These are just some small tweaks. You have to add a bit more to the statement. You can't just say that the statement is the two curves E0 and E1. You have to actually provide some points. And these are points of order 3 to the n. So I'm proving knowledge of a 2 to the n isogeny. And to do that, I have to give some points of order 3 to the n. I have to give a basis for the 3 to the n torsion on E0. And I have to give its image under my witness. And the prover, the honest prover, behaves the same way. Just does the two vertical things, but the commitment has to include not just the two curves E2 and E3, but also the image of a basis. So the prover could choose a random basis of E2 and give its image, but actually for efficiency reasons, we just let there be a canonical public basis that there's just an algorithm that generates a basis on E2, and we have to give the image of those points under phi prime. And now when the challenge is 0, the prover, so normally the prover would just reveal the vertical lines. Well, that's still the case, but it does this in a very special way. It doesn't just reveal the vertical lines. It reveals a pair of integers that generates the kernels and shows that it really proves that these two vertical lines are parallel, right? It says that the kernel, the way I construct the kernel of the left-hand vertical map is the same way I construct the kernel of the right-hand map. So this is, the reason for doing this is really to show not just I know two vertical maps, but I'm convincing you they're parallel. You should not be convinced in the audience yet. This needs some proof that this is sufficient. And when the challenge is 1, normally I would answer with the horizontal at the bottom. I answer with the horizontal at the bottom, and you check. Not only is it a map from E2 to E3, but you check that it's mapping the points the right way. That when you recompute this canonical basis, you compute the image of the point, it goes to the right place. So these are the extra little tweaks we have to add to the protocol. And in the paper, we explain that these tweaks are enough. And again, if you can repeat the protocol many times and you're always convinced, then these are enough to prove that that all the kernels match and there really is an isogeny of the correct degree. The zero knowledge now becomes more complicated because the commitment has more things in it and the responses have more things in it. So it's harder to simulate this. So we have to have more computational assumptions because the simulation is non-trivial. I'll skip the assumptions because I'm out of time. So it's an open problem to do better. Yeah, and then the soundness, you really have to work through the soundness to show that it proves something. Okay, I will skip over the bicycle wheels. The bicycle wheels are saying, do you need to do this? Can you avoid this? And I don't know. That's an open question. All right. This is the icing on the cake. This is really the big result. We've come up with a protocol that does prove knowledge of an isogeny of the correct degree from E1 0 to E1. But what I would really like to do is not just prove that it has the correct degree, but also prove that it's mapping these points to the correct points. If you have that, then you get non-interactive key exchange from SIDH, which is a hard. I mean, there are solutions to this problem, but none of them is very good. So we really like to be able to prove correctness of the points. And we managed to solve this in the paper, and it's really complicated. It's that complicated, and I don't really want to go through it. It's you have to double the commitments. You have to show also some stuff. The horizontal lines are parallel. The verification algorithm involves verifying all sorts of stuff. This is verifying the challenge zero case. You've really got to check a whole bunch of stuff. It's more complicated than I would have liked. And we really had some errors. The first version of the paper had some errors in the zero knowledge. Our simulation wasn't well. Our simulation was based on a computational assumption that wasn't actually sound. So I mean, it wasn't true. So there's definitely, this was non-trivial. But I think by the end of it, we do have something which is plausibly zero knowledge, and we do have a very, I think, a very elegant proof that it's sound, so that you really can, if you can get responses to the two different challenges, then you've got a very nice argument that not only do you know that there's an isogeny of the correct degree, but the points do map to the correct points. It's still not efficient because you're still dealing with these single bit challenges, and that really sucks. And some of the other things, when I put out that one slide that gave you the whole kind of overview of the state of the art, there are some things in there that are getting away from single bit challenges. There we've got C-sign, and some of these things allow larger challenges, but the really big one is ski-sign. Ski-sign only has a single challenge from an exponentially large challenge space. So that's really very interesting. But it's not a proof of knowledge. There's no extractor, it's just a signature scheme. So there's lots of open questions. There's trying to get away from these single bit challenges to more practical schemes. I've got no clue about that. It would be good to understand the computational assumptions that are needed for zero knowledge. There are these questions about the multiple edges and the bicycle wheels that I think are interesting mathematical problems. And yeah, fundamentally, is there a simpler, do we really need all the stuff in the slide? I'd love to believe it, but the only reason we got there is because every time we had something simpler, it wasn't secure, so we kept having to add things, and that's how it ended up. But it is a bit painful, and I'd love there to be a more simple solution to this problem. So lots of work to do. So I'll stop there so we've got time for questions.
Yeah, thank you very much, Stephen. I think this is really, really interesting. There is a question in the chat. It's from Vanessa. Thanks for a great talk, Stephen. Is it easy to give intuition for why phi p and phi q don't leak information about phi? Is it the main hardness assumption?
This is exactly, yeah, this is the SIDH, and it's really important that the orders are different. So you're giving the image of points whose order is a power of 3 under a map whose degree is a power of 2. And so the idea is this sort of, you can think of this as almost like a Chinese remainder kind of thing going on. You're giving information about some other sort of modulo different prime through maps. Because if you send images points of order 2 to the n through a map of degree 2 to the n, then it would completely leak. But yeah, this is basically the fundamental assumption underlying SIDH, and we actually don't really have evidence that it's hard. That's an assumption, but quite a strong assumption. And actually, that's led to lots of attacks. So not attacks on the fundamental primitive, but there are these adaptive attacks and things that I've worked on are all based on the fact that you're sending not just a curve, you're sending a curve and some points, and so you can play dirty tricks with these points and attack honest players by using this. So it's sending the points is annoying, and these other isogeny schemes, C-side, don't send the points, And everything is kind of cleaner in the seaside world and simpler. N and prime, otherwise, yeah, no, it doesn't matter about N and M. It's just a large power of 2 and a large power of 3. The actual power doesn't matter.
So this answers the next question. And then there is another one in the original ZK proof, which was vulnerable to malicious attackers who could give a different isogeny from E0 to E1. Is there any clear way how they constructed these different isogenies?
Yeah, so it's not so easy. Yeah, so the way you do it is you start with a curve. You sort of start with the E2. So you start with the curve E2 with an automorphism. You take an isogeny to E3, and then if you precompose with the automorphism, you get a different isogeny from E2 to E3, and then you have to sort of go backwards and work out what the E0 and the E1 are. So you can create examples for your paper to show that it's non-trivial. But that was one of my open questions. My open questions was, does this really happen in practice? So in theory, it does, but it's not clear to me that it's actually a threat that well, I think it's an interesting question to study as to whether that's a realistic threat in SIDH or not, in the sense that people could actually construct examples that made it a problem.
I actually had a question. I was going to ask about this exponential challenge space issue, but you already answered that. Also, this kind of like the issue that you mentioned, this extracted witness not having the correct order, that kind of reminded me of this issue in the lattice setting where we want the solution to be short. And if we don't prove that it's really short, then it's kind of not meaningful.
Yeah, exactly. And it's exactly that it comes up in the lattice world, right? Because in the lattice world, you have signature schemes that are, they're definitely proving, it's hard to forge signatures based on some computational assumption, but the signature is not a proof of the private key. The assumption in forgery is finding a vector that's maybe quite a lot longer than the actual vector of the private key.
I think, sorry, I got disconnected for a minute. Were you answering my question, Stephen?
Yeah, sorry. Yeah, I was answering your question. It was the fact that you have in signature, a signature is not a proof of knowledge. A signature is forging a signature is solving some computational problem. It doesn't prove knowledge of the private key. For lattice signature schemes, you don't have an extractor that turns a forger into something that computes the private key. You just turn the forger into something that solves a different computational problem. And that's exactly what's happening in ski sign, for example. So ski sign, the private key is a specific isogeny of a certain degree. And you show that if you've got a forger, it's computing an endomorphism. And so they're they're related problems, but they're not the same problem.
Yeah. Do you have a question?
Yeah, I was actually going to ask also about this. So this isogeny of different degree that the extractor can compute, is that still a hard problem to compute such a isogeny?
Yeah, I mean, the slight subtlety with isogenies is that there's a lot of the computational problems are kind of morally equivalent in some sense. So if I can compute one isogeny between two curves, then I can also, so how does it usually work with isogenies? There's always a special curve, and we know kind of everything about it, and we know it's endomorphism ring. And so if I can compute an isogeny between that special curve and a random elliptic curve, then I can also work out the endomorphism ring of this other curve. And then somehow, once I know the endomorphism rings of these two curves, I've got total knowledge, and I can now compute all sorts of other isogenies between them, and I can find isogenies of a special degree and all sorts of stuff. So if in the example, in the Soundness counterexample, I was a little bit disingenuous because I said a cheating forger can, well, I wasn't disingenuous, but a cheating forger or a cheating prover can certainly construct two curves that are not related by an isogeny of degree 2 to the n, and fool the verifier. But the verifier does learn an isogeny between those two curves. And if the first one was one of these special ones where everyone knows the endomorphism ring, then that verifier would also be able to compute the endomorphism of the second curve. And then once they knew that, they'd be able to verify for themselves, hang on a minute, there is no isogeny. Like you can detect whether there's an isogeny of a given degree between two elliptic curves if you know the endomorphism ring. So they could actually realize they'd been fooled by the time they'd completed the proof, if they were suspicious. Or if there was, in the Gantos thing, if there was a witness of the correct degree, but the prover was cheating, again, once you've got some isogeny, if you could get some isogeny between the two curves, again, you'd end up being able to work out the isogeny between them. But that's going way outside the proof and using a whole bunch of other algorithms that come up in isogeny crypto. So, within what you really want is just the honest verifier to be able to follow the steps, follow the manual, and be convinced that they're not being fooled.
Okay, thanks.
If there are no further questions, we may conclude the session here. Thank you very much, Stephen. Yeah, this was very interesting. Yeah, it seems like there are lots of questions to be studied.
Definitely. There definitely are. I mean, some of them I hadn't even thought of until giving the talk this week.
Yeah. So once they are solved, I think it might be a game to give a follow-up talk.
Yeah. Oh, that's good.
Yeah. Thank you, everyone.
Sorry, I wanted to be late.
Thank you again, Stephen, and hope to see everyone.
It's all right. No problem. Bye-bye.
Bye-bye.
Bye-bye.